Welcome to Session 17, Probability, Conditional Reasoning, and Counting. This lesson develops mathematical reasoning that stays reliable when a problem looks unfamiliar. You will learn to define the correct sample space, to apply conditional and addition rules, and to decide whether order matters. These are connected habits, not isolated tricks. Keep a pencil ready. We will build a mental model, use a repeatable method, solve a demanding example, diagnose an error, and finish with an independent checkpoint. Start with this principle. Probability errors usually begin with the wrong sample space. Use this visual structure. Condition is greater than restrict OR is greater than ADD. Overlap AT least ONE is greater than complement. Read every symbol and label before calculating. The first goal is to define the correct sample space. Connect it to the second goal. Apply conditional and addition rules. Correct calculation begins with correct interpretation. When the surface details change, search for the same relationship underneath. Transfer means choosing the structure from evidence rather than waiting for a familiar-looking example. Step 1. Name the event and denominator. State the target and preserve its units or conditions. Step 2. Restrict the sample space when conditioned. Use a separate line so signs, factors, and labels remain visible. Step 3. Correct for overlap or use a complement. Keep the reasoning efficient, but never skip an operation that could hide an error. Step 4. Check probability bounds or count integrality. Verification is part of the solution because it tests the answer from another direction. Signal 1 is given or among. Respond by remembering, change the denominator, name the response before calculating. Signal 2 is A or B. In that case, subtract overlap once. The form tells you which tool fits. Signal 3 is distinct roles. Remember, use permutations. This separates plausible work from valid reasoning. If you cannot name the signal, pause and classify. A deliberate choice of method is usually faster than repairing a rushed setup. Here is the challenge. Two independent events have probabilities, 0.6 and 0.5. What is the probability both occur? Restate what is requested before touching the choices. The first move is, name the event and denominator. Apply it directly to the quantities and conditions in this problem. Now use the core reasoning. For independent events, multiply 0.6, 0.5 equals 0.3. Keep each equality, comparison, or unit conversion visible. Pause for a midpoint audit. Check copied values, signs, units, restrictions, and whether the current result is the requested quantity or only an intermediate value. Continue by applying this control, correct for overlap, or use a complement. The explanation supports one option without relying on its position. The mathematical conclusion is 0.30. State it with any required units, interval notation, or restrictions. The final answer is 0.30. Compare it with the exact target and reject any choice that represents a common intermediate step. Verify from another direction. Enumerate a small sample space, or verify with a two-way table. The check should use evidence independent of the original calculation whenever possible. Try this checkpoint without copying the example. Why must every computed probability be between 0 and 1? Decide which mathematical fact controls the answer. Pause and write one line of reasoning before committing. A visible decision is easier to inspect, explain, and correct than an unsupported guess. Focused hint. Values below 0 or above 1 cannot represent a valid share of a sample space. Use the hint to repair the setup, then finish the reasoning yourself. The accepted answer is probability represents a fraction of possible outcomes. Explain why it works, and name the earliest line that would reveal a likely error. The central message is to define the correct sample space. Combine that with the discipline to apply conditional and addition rules. Finish by remembering to decide whether order matters. A result becomes dependable only when the method and verification are both clear. Reflection. What exactly belongs in the denominator after the condition is applied? Name the exact point where an incorrect path would first become visible. Practice one fresh problem for 8 to 12 focused minutes. Keep the work readable, verify independently, and carry the routine into the next session. Before moving on, close the notes and explain the method aloud from memory. Then invent one small variation, predict how the answer should change, and verify that prediction with a complete calculation.